Welcome viewers to the fourth and the last segment of the fifth lecture for the online series of lectures for the course of linear algebra. In this last segment, we'll state and prove Theorem 4, and there will be a corollary to this theorem that will also prove. So let me state Theorem 4 first, and then I'll prove it. Theorem 4. Let V be a vector space over F, which is spanned by a finite set of vectors u1, u2, all the way up to um, then any independent set of vectors in V is finite and contains no more than m elements. Okay, right. So here is the proof of this theorem. It suffices to show that any set S containing more than m elements is linearly dependent. Okay. All right. Suppose in S there are distinct vectors v1, v2, all the way up to vn with n greater than m. Okay, so there are more than m distinct vectors in S, right? And we are denoting those n distinct vectors as v1, v2, all the way up to vn. Since the vectors u1, u2, all the way up to span V, there are scalars aij such that each vj can be written, each of these vj's here, j running from 1 to n, can be written as a linear combination of these m vectors, okay, where the coefficients of the linear combination are given by these aij's. Okay, so let me write the linear combination aij ui, okay, where I runs from 1 to m. Okay, So we see from here that each of these VJs is a linear combination of these M vectors, U1, U2, all the way up to UM. Okay, now I need some space. Let me erase the statement. For given n scalars, x1, x2, all the way up to xn, we have x1 v1 vector plus x2 v2 plus all the way up to xn vn. Okay, just taking an f linear combination of these n vectors, okay, which is in the summation notation xj vj, j running from 1 to n. Okay, now since each of these vj's are written as a linear combination of ui's, let me substitute vj with this sum in this expression, j from 1 to n, xj, and then this sum, I from 1 to m, aij, ui. Okay, so now this is the same as j equal to 1 to n and I equal to 1 to m, aij, xj, ui. Okay, let me erase this bottom content. So this is nothing but I'm just taking away the sum over I, and then this is sum over j, aij, xj times ui. This is equation number 21. Okay, so given the m times n matrix A, whose entries are precisely the coefficients of this linear combination. Okay, remember that we wrote each of these VJs as a linear combination of the UIs. Okay, and these coefficients are precisely the entries of this matrix A. So given the m times n matrix A with entries aij, okay, over the field F, and the n times 1 matrix X with entries xj, right? J equal to 1, 2, all the way up to n. The ith row AXI. Okay, AX is a column vector, right? AXI of the M times 1 matrix, which is a column vector. AX is given by AXI is equal to AIJ XJ, J running from 1 to N. Okay, this expression here. This is equation number 22. Okay. Now, by Theorem 2 of Lecture 3, since M is less than N in the matrix A, so remember that A is an M times N matrix, okay? And since M is less than N, as required in the second theorem of Lecture 3, for the M times N matrix A, the homogeneous system of linear equations AX is equal to 0 is a zero matrix, right? On the right side we have a zero matrix of size M times N, which is a column vector with M components. Okay, and the left side, on the left side, this is M times N and this is N times 1, so that we have a N times 1 matrix on the left side, and we set that M times 1 matrix to the 0 matrix, M times 1 0 matrix. Okay, so this is a homogeneous system of linear equations, and this equation has a non-trivial solution according to Theorem 2 of Lecture 3. I suggest that you go back to Lecture 3 and consult Theorem 2 there. It has a non-trivial solution. This system has a non-trivial solution. We know that trivial solution is always a solution for a homogeneous system of linear equations. The question remains if it has a non-trivial solution, but it's guaranteed that it has a non-trivial solution if for the matrix A, if for the M times N matrix A, M is less than N, then it's guaranteed that there is a non-trivial solution. Okay. Now, in the component form, this reads off as this guy reads off as sum over Aij xj as j runs from 1 to n. So we get So this is 0, 0 all the way down to 0. So there are m zeros here in this column vector, right? And this is, we set this to be one of these zeros, okay? So this is the ith row of this column vector. A times x is a column vector, m times 1 matrix, right? And the ith row of this column vector is set to 0. Okay, I runs from 1 to m. This is our equation number 23. So this matrix equation translates to this equation component wise. Okay, this is the story of one of the components of this, m times 1 matrix. Similarly for the left hand side. Okay, and so this has a non-trivial solution, means that this holds when not all of the scalars x1, x2 all the way up to xn are 0. Okay, this is what we mean by the system admitting a non-trivial solution. Okay, when they are all 0, okay, when this vector, this column vector is identically 0, then that's a trivial solution. We know that is always a solution of a homogeneous system of linear equations, but from the theorem it's guaranteed that it has a non-trivial solution. So we have a solution for which not all of these components are identically 0. Okay, good. So therefore from this equation number 21, so let me write equation number 21, but before that I need some space. Let me erase it. So what was the equation number 21? Let me write it for you here. It was x1 v1 plus all the way up to xn vn, and that is equal to, we found that this expression is equal to the sum over I from 1 to m, and inside which I have the sum over j running from 1 to n aijxj times ui. Okay, this was equation number 21, and this is equation number 23. Okay, so therefore from 21 and 23 it follows that x1 v1 plus, so this is important, that in this expression not all of the xj's are 0. Okay, x1 v1 x2 v2 all the way up to xn vn is equal to 0 vector if and only if this guy here is 0, right? And this has to be 0 for all the i's. This is important. If and only if this sum is 0 for all I belonging to this finite set. Okay. All right. And we know that so by theorem 2 of lecture 3, it has a non-trivial solution. Non-trivial solution, right? These means there exist scalars x1, x2 all the way up to xn, not all of which are identically 0, identically 0 such that x1 v1 plus all the way up to xn bn is equal to the 0 vector. Okay, so we can find such scalars x1, x2 all the way up to xn such that they are not, they are not all identically 0, and this holds. It means that the set S, therefore the set S v1, v2 all the way up to vn is a linearly dependent set. Okay, so the fact is that since n is greater than m, we are able to apply this theorem 2 from lecture 3. That fact, n being greater than m, that fact enables us to apply theorem 2 from lecture 3. Okay, QED. So let me erase everything now. We have 2 corollaries of theorem 4. So the first corollary 1 to theorem 4, states that if V is a finite dimensional vector space, remember that the finite dimensionality of a vector space is equivalent to the fact that it has a finite basis. Okay, so if V is a finite dimensional vector space, then any two bases of V have the same number, of course finite, okay, because it's a finite dimensional vector space. They have the same number of elements. Okay, this is the statement of corollary 1 to theorem 4. Let us prove it. Since V is a finite dimensional vector space, it has a finite basis, right? Finite basis. Let us denote this basis with the set u1, u2 all the way up to um. Okay. Since the above set is a basis, it spans V, right? We know that a basis is a spanning set, and it is also a linearly independent set. Okay, and therefore it spans V. In other words, V is spanned by, V is, to phrase it in an equivalent way, V is spanned by the finite set of vectors u1, u2 all the way up to un. Okay, there are m many vectors in this set, and V is spanned by these vectors, by this set. Therefore, by Theorem 4, which we proved a while ago, by Theorem 4, every basis of V, is finite and contains no more than m elements, and contains no more than m elements, right? Good. Thus, if this set V1, V2 all the way up to Vn is a basis of V, then n is less than or equal to m. Okay, n has to be less than or equal to m. Otherwise, it won't be a linearly independent set according to Theorem 4. And hence will not be a basis. So if V1, V2 all the way up to Vn is a basis of V, then n must be less than or equal to m. Okay, now I need some space here. Now, if V1, V2 all the way up to Vn is a basis of V, then according to the definition of a basis, V is spanned by the finite set of vectors this finite set of vectors v1, v2 all the way up to vn. Then by Theorem 4, So we started with the assumption that this guy is a basis. This guy is a basis, right? Remember that this was the starting assumption, that this guy is a basis of the finite dimensional vector space V, right? So according to Theorem 4, the finite basis this finite basis U1, U2 all the way up to UM, which is a linearly independent set, of course, because it's a basis, right? It cannot have more than n elements, because this is a set that spans V, and since it is a linearly independent set, it cannot have more than n elements in it, okay, which means that m is less than or equal to n. The finite basis can't have more than n elements in it, right? That is, m is less than or equal to n. Okay, so we proved earlier that n is less than or equal to m. Now we proved that m is less than or equal to n. Together they mean that m is equal to n. Okay, QED. Okay, now an important result, which is a consequence of this corollary 1 to theorem 4. This corollary allows us to define the dimension of a finite dimensional vector space. Vector space as the number of elements in a basis of V. Okay, because any basis of a given finite dimensional vector space has the same number of elements, and that is called the dimension of that finite dimensional vector space. Okay, right, now it's time to reformulate theorem 4 in a convenient way, and that is going to be the second corollary to theorem 4. We now reformulate theorem 4 as follows. This is corollary 2 to theorem 4. Let V be a finite dimensional vector space, and also let n to be equal to the dimension of the vector space V, meaning that there are precisely n elements in any basis of this finite dimensional vector space. Then A, any subset of V which contains more than n vectors, n vectors is linearly dependent. Okay. So if a basis contains n elements, then if you have a set of vectors containing more than n elements, that set cannot be a linearly independent set. It will be a linearly dependent set. Okay. Linear independence will be compromised if the number of vectors of the set you choose is greater than the number of elements in a basis. Okay, so the linear independence is going to be compromised in that case. Okay, because for a basis you both need the linear independence and the spanning condition. Okay, so the linear independence condition is going to be compromised if your number of vectors is more than the number of elements in a given basis. B, no subset of V which contains fewer than n elements can span V. Okay, if the number of elements is smaller than the elements in a given basis, then those elements in the given set will not span the vector space. Okay, so the spanning condition is being compromised when the number of vectors is smaller than the number of elements in a given basis. Okay, good. So let us prove this this corollary 2. Part A is simple. Okay, it's a consequence of corollary 1. Let u1, u2, um be a set of m vectors with m being greater than n. Okay, that is, the set above contains more elements than the number of elements or vectors in a basis. Say the basis is given by this set v1, v2 all the way up to vn of an n-dimensional vector space V. Okay, since v1, v2 all the way up to vn clearly spans V, and m, okay, the number of elements in this set m is greater than n, by theorem 4 the set u1, u2 all the way up to um can be a linearly independent set. Can't be a linearly independent set by theorem 4. Okay, so it's a consequence of theorem 4, not to the first corollary of theorem 4. Okay, so my mistake. So the part A is a consequence of theorem 4. Okay, corollary 2 of theorem 4. Okay, now part B. So let me erase everything. I'm going to prove part B. If a set has fewer than n elements, then the set is not going to span the vector space V. Okay, that's what I need to prove. Suppose, as in part A, that V1, V2, all the way up to Vn is a basis of the vector space V. Basis of the vector space V. Now let W1, W2, all the way up to Wm be a set of vectors in V with m less than n. Okay, so this set has fewer elements than the elements in a given basis of the vector space V. Okay, I want to show that W1, W2, all the way up to Wm does not span V. Okay, this needs to be proved. Now let us proceed by contradiction. Proceed by contradiction and suppose instead that W1, W2, all the way up to Wm span V. This set spans V. Okay, then each of the vectors in this set, okay, in V1, V2, all the way up to Vn can be expressed as a linear combination of the vectors, as a linear combination of the vectors in W1, W2, all the way up to Wm. Okay? Okay, it follows from the definition of the subspace spanned by a given set of vectors. Okay, so let us express V1 as a linear combination of these m vectors, the coefficients of linear combination being a11, a12, all the way up to a1m, a11w1 plus a12w2 plus all the way up to a1m wm. That's V1. And V2 is equal to a21 w1 plus a22 W2 plus all the way up to A2M WM. Okay, finally Vn is equal to AN1 W1 plus AN2 W2 plus all the way up to ANM WM. Okay, this is what we have. Now we want to write it in the matrix form. Let me erase this part because I need room, a lot of room actually. Write it in matrix form so that so I write it as a row vector, although each of the entries, each of the components of the row being a vector, which you can think of as a column vector, v1, v2 all the way up to vn is equal to w1, w2 all the way up to wm, and then I have this matrix a11, a21 all the way up to an1, a12, a22 all the way up to an2, and finally the last row being a1m, a2m, okay, all the way up to ann. This is our equation number 23. Okay, so you see that the matrix form of this equation is this equation number 23. Okay, so let me erase this equation now. Okay, good. Now since m is less than, so here you see that well, we took m to be less than n, right? M to be less than n. All right, since m is less than n, the following system has a non-trivial solution. The following system has a non-trivial solution by theorem 2 of lecture 3. Again, we use the theorem 2 of lecture 3. Okay, and the non-trivial solution is given by x1 equal to b1, x2 is equal to b2, all the way up to xn being equal to bn, which means that not all of these scalars b1, b2 all the way up to bn are identically zero. Okay, so in the matrix form, this homogeneous system of linear equation is given by a11, a21 all the way up to an1, and then I have a12, a22 all the way up to an2, and finally a1m, a2m all the way up to anm. Okay, and this multiplied with this column vector x1, x2 all the way up to xn. Okay, this is an m times n matrix, and this is an m times n times 1 matrix, so the resulting matrix is going to be an m times 1 matrix, and I set it to the column vector, or it's a zero matrix of size m times 1. Okay, so this is our homogeneous system of linear equations, and since m is less than n, this homogeneous system of linear equations also admits the non-trivial solutions, and we assume that the non-trivial solution is given by this. Okay, where not all of these scalars pi's are identically zero. Okay, now let me erase this part, equation 23, so that so since this is the solution of this system, this matrix A11, A21 all the way up to AN1, A12, A22 all the way up to AN2, and finally we have A1M, A2M all the way up to ANM. This matrix multiplied by B1, B2 all the way down to Bn is equal to this zero matrix of size m times 1. This is our equation number 25. Okay, now multiplying, so get back to equation number 23. I had to erase it because I needed room. So get back to the equation 23. So, and we multiply both sides of equation. So get back to equation. So we denoted that equation, we numbered that equation with 23 prime, and multiplying both sides of 23 prime by this column vector b1, b2 all the way down to bn. On the right, one gets v1, v2, vn times this column vector b1, b2 all the way down to bn is equal to w1, w2, wm, right, times this m times n matrix a11, a21, an1, a12, a22, an2, a1m, a2m all the way up to anm times b1, b2, bn, okay, which boils down to b1, v1, so I'm multiplying these two vectors, to have b1, v1 plus b2, v2 plus all the way up to bn, vn is equal to the zero vector, because this guy is an m times 1 zero vector, right? So that we end up with a zero vector here. okay, where not all the BI's are identically zero. Okay, hence the set V1, V2 all the way up to Vn, this set is a linearly dependent set, linearly dependent set. Okay, this set is a linearly dependent set, contradicting the fact that V1, V2 all the way up to Vn is a basis of the vector space V. Okay, and we are done. QED. Alright, good. So this is the end of lecture 5. Thank you for attending the 5th lecture.